Welcome back. In this module, we will develop the necessary mathematical tools to describe simultaneous processes of diffusion and reaction of substrates inside the biofilm. Substrate and oxygen concentrations within the depth of the biofilm will be different from concentrations in the bulk water. For oxygen, it turns out we have microelectrodes that can be used to directly measure oxygen concentrations at different locations within the biofilm. On the lower left, you see the tip of such a delicate sensor that is only a few micrometers in diameter, not much larger than the diameter of a microbial cell. Researchers have grown biofilms in flow chambers and measured oxygen concentration profiles under a microscope. Now here's an example of such a measurement. This slide is showing two concentration profiles for two different bulk phase oxygen concentrations. We can see that increased bulk phase oxygen concentrations lead to higher oxygen concentrations inside the biofilm. How can we capture these features in a mathematical model? By the end of this module, you should be able to explain relevant processes determining concentration profiles of substrate inside the biofilm. Key processes are diffusion and biological degradation. You should be able to derive mass balance equations considering diffusion and reaction in the biofilm. And you should be able to calculate substrate concentrations inside the biofilm and substrate fluxes into the biofilm, assuming first-order degradation kinetics. Our goal is to step-by-step develop the mass balance that allows us to model substrate concentrations within the biofilm. Here, we're starting out with the typical concentration profile. Bulk phase substrate concentrations we refer to as SB. The substrate concentration within the biofilm we refer to as SF. We're now introducing a new coordinate system where x is the distance from the surface of the biofilm. Thus, x equals 0 at the surface of the biofilm and LF at the base of the biofilm. In this system, we now introduce J sub F, which is the flux of substrate at a given location x. Flux means the transport of substrate at a given distance from the surface of the biofilm per unit area and per unit time. The red arrow indicates the direction of the flux. Fick's first law states that the flux always goes from the region of high concentration to low concentration. And flux increases with increasing concentration gradient. Now we've introduced the key terminology and key concepts of mass transport by diffusion that we need to model biofilms. And now let us translate these concepts into mathematical equations. The term on the right-hand side of this equation is the substrate concentration gradient at location x. The concentration gradient, or we can also refer to it as the slope at location x, is also shown in the schematic. If we multiply the concentration gradient with the constant, the diffusion coefficient, then we can calculate the flux. In this slide, there is another feasible plot of substrate concentration inside the biofilm. If the concentration gradient, as shown here, is smaller, then the flux will also be smaller. If the gradient is 0, then the flux is also 0. Here we see a case with the constant concentration throughout the biofilm. A constant concentration means that the slope is 0, therefore also the flux at every location. This steady-state concentration profile represents the situation where there's only the process of diffusion, but no degradation of substrate in the biofilm. Now, let's take a closer look at the base of the biofilm. At the base of the biofilm, bacteria grow on an inert carrier material. Substrate cannot diffuse into this carrier material. In other words, the flux at the base of the biofilm must be zero. And if the flux is zero at the base of the biofilm, then also the concentration gradient must be zero. This corresponds to what is shown in this figure. In the previous slide, we discussed how to make use of Fick's first law to calculate fluxes. Now we go one step further. We look at the substrate flux at location x and at location x plus delta x. With this, we define a control volume and we do mass balance for this control volume. We evaluate the situation assuming steady state. Substrate diffuses into and out of the control volume. We use Fick's first law to quantify this. These are the first two terms on the right-hand side of the equation. The third term is the equation describing substrate degradation within the control volume. This equation already now provides very useful information. If the degradation is larger than zero, then the rate of substrate diffusing out of the control volume must be smaller than the rate of substrate diffusing into the control volume. Thus, as we're moving away from the surface into the biofilm, the slope of the substrate concentration profile must get smaller and smaller until the slope becomes zero at the base of the biofilm. This expectation is consistent with the substrate concentration profiles we have been sketching all along. We can rearrange this equation now assuming steady state. If we then let delta x go to zero, we obtain the mass balance for mass transport within the biofilm for steady state conditions. The first term in this equation considers changes in the substrate flux at location x. This is represented now by the second derivative of the substrate concentration. The second term is the substrate degradation at location x. We will be using this equation throughout the course. Thus, here is a larger version so that we can remember it well. In case we want to consider dynamic systems, then we can also extend this equation by considering an accumulation term on the left-hand side of the equation. How to solve this equation? We will need to decide on a suitable rate expression for the substrate degradation. This rate expression could be a zero-order rate expression where the substrate degradation rate is independent of the substrate concentration. Or it could be first order. Or we could consider monokinetics. And ultimately, we can consider more complex and coupled kinetic expressions as we have gotten to know from activated sludge modeling. From activated sludge systems, we are very used to work with mono or more complex kinetic expressions. But unfortunately, there are no analytical solutions for the biofilm if we assume monokinetics. Thus, we will start working with simpler kinetics and derive analytical solutions. These analytical solutions will be very useful for developing a better understanding of mechanisms driving biofilm processes. Then later in this course, we will introduce the use of simulators that are readily available and that provide numerical solutions to the biofilm equations. Then we're no longer limited by the availability of analytical solutions. In the current module, we will focus on solving the biofilm equation for first-order kinetics. We assume steady state. We then have a second-order differential equation. To solve this second-order differential equation, we need two boundary conditions. Boundary condition number one, the substrate concentration at the surface of the biofilm, x equal to 0, is equal to the bulk phase substrate concentration. Boundary condition number two, the substrate gradient at the base of the biofilm, thus at x equal to LF, must be 0. We had discussed this boundary condition earlier in this module when we discussed that the biofilm carrier is not permeable for substrate. And then we consider our first order kinetics, where substrate degradation rates are linearly dependent on substrate concentrations at that location. Here's the mass balance equation, and here's the solution. This is excellent. We now have an analytical solution for substrate concentrations within the biofilm, SF, as a function of the bulk phase substrate concentration, SB. This analytical solution considers X, the location within the biofilm. It includes the biofilm thickness, LF, and it includes another constant, L crit. L crit considers the diffusion coefficient, dF, and the rate constant, K1F, times XF. Here, XF is the biofilm biomass density, and K1F is the first order kinetic constant. Here's a graphical representation of the biofilm solution we derived in the previous slide. On the y-axis, I am plotting biofilm concentrations relative to bulk phase concentrations. On the x-axis, I'm plotting the location X relative to the total biofilm thickness. The different curves in this plot are solutions for different values of LF over L crit. LF over L crit increases with increasing biofilm thickness, with increasing biofilm biomass density, with increasing rate constant, and with decreasing diffusion constants. As we can see in the plot, with increasing values of LF over L crit, substrate can penetrate the biofilm less and less. How useful is this solution for the substrate concentration inside the biofilm? We do get information on the local availability of substrate for bacteria to survive. This information is useful for better understanding. But for practical reactor operation, we're in fact more interested in how effective this biofilm is in removing substrate from the bulk water. For this, we must now calculate the flux of substrate into the biofilm. Luckily, we have already introduced the tools we need to calculate substrate flux from substrate concentrations, or to be more specific, from the gradient of substrate concentrations. To calculate the flux at the surface of the biofilm, x equal to 0, we must determine the substrate gradient at the surface of the biofilm. With the analytical solution of the substrate concentration profile, we can simply take the first derivative to obtain the concentration gradient. Here is the flux at every location within the biofilm. To obtain the flux at the biofilm surface, we simply choose x equal to 0, and we obtain the following solution. Here I'm plotting the substrate flux into the biofilm, JLF, on the y-axis, and on the x-axis, I'm plotting the bulk phase substrate concentration. As we can see, the overall substrate flux is linearly dependent on bulk phase substrate concentration SB. Thus, first-order kinetics inside the biofilm lead to overall first-order dependence of the substrate flux on bulk phase substrate concentrations. Let us now do an example using the tools we have developed. Let us design a biofilm reactor assuming the following situation. Influent substrate concentration of 200 milligrams COD per liter, effluent COD concentration of 3 milligrams COD per liter. Here, we assume that the substrate is acetate. An influent flow rate of 1500 cubic meters per day. We assume a moving bed biofilm reactor with a specific surface area of 300 square meter per cubic meter. And we assume typical kinetic and biofilm parameters as summarized in example 17.1 in our textbook. 400 micrometers thick biofilm, first order rate constant of 2.4 cubic meters per gram COD and day, biofilm biomass density of 10,000 grams COD per cubic meters. Finally, also the diffusion coefficient of acetate in the biofilm. With this information, we should now be able to design a biofilm reactor based on microbial kinetics. First, we calculate the value of L crit. For our example, L crit equals 58 micrometers. Using L crit, we can calculate the value of LF over L crit. Earlier in this module, we plotted substrate concentrations over the thickness of the biofilm. Very low substrate concentrations inside the biofilms were observed for biofilms where LF was significantly larger than L crit. Based on this, we expect a steep decline of substrate concentration into the biofilm, also in our current example. But for this design example, we are not so interested in these substrate concentration profiles inside the biofilm. Instead, we want to calculate the substrate flux going into the biofilm. This is here the flux equation that includes LF over L crit. Using the information we have, we now calculate a substrate flux into the biofilm of 4.1 grams COD per square meter and day. We now introduce the substrate flux we've calculated from the microscale mass balance of the biofilm into the macroscale mass balance of the overall reactor. From this, we calculate the necessary biofilm surface area, capital AF, of about 72,000 square meters. Next, we calculate the necessary reactor volume by dividing the biofilm surface area by the specific biofilm surface area, and we obtain a volume of 240 cubic meters. To get a better feel for the design, we calculate the hydraulic retention time, which turns out to be 3.8 hours. In our textbook, Table 17.3 provides a summary of relevant analytical solutions for the diffusion reaction kinetics in the biofilm. Here's a close-up of Table 17.3, focusing on first-order kinetics inside the biofilm and calculating the corresponding substrate flux. As shown in the previous example, we first calculate the value of L crit. Combining L crit with the biofilm thickness, LF, and the diffusion coefficient, dF, we can calculate a new constant, K sub 1a, to directly calculate the substrate flux. Here's the overall table 17.3 with solutions for first-order kinetics. In the next module, we will be deriving solutions for zero-order kinetics inside the biofilms. These are also included in table 17.3. Thus, table 17.3 will be very useful for you throughout the overall course. Here are the take-home messages from the current module. We have derived the second-order differential equation to describe diffusion and reaction inside the biofilm. We've derived analytical solution for first-order kinetics for substrate concentrations inside the biofilm, SF, substrate flux into the biofilm surface, JLF. And we've observed that first-order kinetics inside the biofilm result in overall first-order kinetics of the substrate flux into the biofilm.